Official members bounce, bust off the chrome. Realize it's real hell where we call home.
Official members bounce, bust off the chrome. Realize it's real hell where we call home.
From the heart inside one, I vision fat licks and mat clips. The chroma make the average imitator do backflips. You lack a pistol, so put a vest around the issue. Slugs will never miss you. Coming from members that's official.
A lot I want to cover today, plus I want to spend time at the end hopefully popping up MySQL and Postgres and throwing real transactions at it so you guys can see that, like, oh, Andy's not making up. This stuff is actually how it works. When we expect what the database does when we run transactions. So quickly, administrative stuff. Project 3 is due this Sunday on the 17th at midnight again. Project 4 will release on this week, I think on Wednesday or tomorrow. The final exam will be Friday, December 13th at 8:30 a.m. I forget where, but I'll announce that. Again, there will not be an early exam. I don't care if your aunt and uncle's 50th wedding anniversary is going to be on a cruise, and therefore, but you already have Taylor Swift concert tickets as well, so you got to go, so you can take the exam. I've heard that before. I don't care. Do not make travel plans. Be there on this date. And then, as I posted on Piazza, if you can't get enough of databases and can't get enough of this class, or you hate databases and you hate BusTub and want to fix it, or you're sadistic and want to make torture the next round of students, make BusTub even worse, don't do that. But please sign up if you want to be a TA with Jignesh next semester. Okay? Any questions about Project 3? All right, and then more database stuff, more talks. Today we're having InfluxDB, the co-founder and CTO. So this is their third talk given at CMU about what they've been building on Influx. The first talk was the new system they were building, told them it was a bad idea, came back the second time, said, Andy, you were right, we're building a new one. And then this third talk is basically saying, oh yeah, here's what we did after we fixed things. And everything's based on data fusion. I'm also hosting Camille Ferreri, who is a SCS alum, I think 2002, 2003. She's coming to get back a distinguished alumni talk. She been in New York City in a lot of executive positions and VP engineering positions for a couple of different companies. She was CTO of Rent the Runway, which is like you rent designer clothing, whatever. And they went IPO. Anyway, she's brilliant. She's giving a talk this Thursday at 4:30 over in Gates, and then next week we'll also have the ClareDB guy giving a talk. Okay, so if you can make to Camille's talk on Wednesday, on Thursday, that'd be great. She's also a PMC for the Apache Zookeeper. Zookeeper is a distributed key value store that's often used for as the backbone for a lot of distributed systems. We'll cover Zookeeper and other systems like that in a few weeks, but she worked heavily on that project as well. Okay? All right, so this slide's wrong. Sorry, wrong slide. All right, but last class we were talking about timestamp ordering, not two-phase locking, right? And the big thing about, I want you to understand timestamp ordering, because we're going to see this today in multi-version concurrency control, is that there's a notion of physical time, like what we'll call the wall clock time of when things actually occur in the real world, when the order of the events in the real world. But then there's also this another notion of a logical time or the commit order of when things actually got saved to the database. And when we saw OCC, there was this private workspace that the transactions were using that was allow them to sort of stage their changes. And then when they went to go commit, then we had that validation step where we had to go figure out, okay, did my transaction miss any updates I should have seen? Or is any other transaction that's still running is going to miss the updates I'm about to make? And we passed sort of the validation steps, then the transaction was allowed to install changes to the global database, and everyone can see them. So what we're going to see today with multi-versioning, it's going to basically look the exact same thing, except now there isn't going to be the private workspace, and the versions are going to hang around in the global database. And depending on how we run transactions, some transactions could see some updates from transactions that haven't committed yet, depending, again, what isolation level we're running at. So conceptually, when you think about what was happening in OCC, that there was multiple versions of tuples, multiple physical versions of single logical tuples in the database. So a logical tuple would be like an object identified by a primary key. Right? A primary key says that there's only one and only one record that can be mapped to this primary key. But then under CC, when I was making changes maybe to that tuple, I had made a copy of it into my private workspace, and now I had another physical version, another physical copy of that single logical tuple. So that's the same idea we're going to do here at MVCC, but now we're just going to do it on steroids, where the database system is going to be allowed to maintain, again, multiple physical versions for a single logical tuple or logical object. So anytime now I want to update something in the database, I'm going to make a new logical version of that object. And in the example that I saw when we talked about OCC, that new version was just a complete copy of the entire tuple into that private workspace. We'll see as we go along that's actually not a good idea, and we can be a little bit smarter about it. Maybe just take copies of the subset of the things that got changed. And then now, when anytime a transaction wants to read that object, it's going to have this view, or we'll call it the snapshot isolation, snapshot view, of the state of the database that existed at the moment that the transaction started. So that means that if another transaction is running at the same time as you are, and but they start after you, and they start making changes, you're not going to see them because you're going to see a consistent snapshot of the database at the moment, the logical time that you started. This makes more sense as we go along. And I'll say also too that we can still combine multi-version concurrency control with two-phase locking and OCC and other protocols that are out there, because multi-versioning isn't just about, oh, I'm making copies of things and maintaining snapshots. We still have to do all the concurrency control stuff we talked about before to figure out who's allowed to update what and when. But now the backbone of the way this architecture is going to work, the system is going to work, is going to be predicated on this idea of I'm going to make versions of things. So MVCC is an old idea. The first sort of what is acknowledged as the first description or implementation of it goes back to this PhD dissertation at MIT in 1978. But that was sort of in like the systems world. And it wasn't until a few years later then people said, oh, this is actually applicable to what we care about in databases with concurrency control. And then it was added into some existing systems. So what is cited as the first implementations of MVCC in a database would be this thing called RDB VMS, and then another system called Interbase. And these are both built at DEC in the early 1980s by this guy, Jim Starkey. He claims he's also the inventor of blobs, like the binary large objects. I don't know whether that's true or not, but that's what he says. And then, actually, who here has ever heard of DEC? Nobody. That was a huge company back in the day, right? The Google of this time. And then they got bought by Compaq, and then Compaq got bought by HP, and now they're basically not really on it. If you ever heard of VAX machines, that's these guys, right? But they were also building databases because they were writing software to run on the hardware they were selling. So these systems are still around today. So Interbase, you can get there's still a company called Interbase, and they sell something that's like a mobile phone embedded database. But the sort of enterprise code was forked off many years ago and open source as this thing called Firebird. If everyone want to know why Firefox is called Firefox, because when Mozilla went under and they wanted to rebrand Netscape, they wanted to call it Phoenix because rising out of the ashes. But there was some other software that had that, so they couldn't call it that. So then they were going to call it Firebird. Couldn't call it that because this database system already exists. So then they came up with Firefox, right? Oracle buys everything, and so Oracle bought RDB from the carcass of DEC, and then they rebranded that as Oracle RDB. So there's the Oracle, the company. There's the Oracle database, the big money maker that everyone is aware of. But then they also call something Oracle RDB. That's the descendant from this DEC machine, right? So Oracle's branding is not very good here. And the Oracle database that everyone knows of is a relational database system. You could call it the Oracle database, a RDB, but it's different from the brand name of this. All right, so now, again, even though this is back in the 70s, pretty much every single database system today, if you're going to build a new one from scratch, is going to be using multi-version concurrency control. All right, so there's two key ideas about MVCC. The first is that the writers are not going to block the readers, and the readers are not going to block the writers. So again, the idea is that when a transaction shows up, they'll be given a timestamp, and that timestamp is going to say, here's the timestamp that allows you to view a consistent snapshot of the database at that timestamp. So you won't see any uncommitted changes, and you won't see if a transaction commits while you're still running, all of a sudden their changes won't materialize because those changes didn't exist at the timestamp you were assigned when you started the system. All right, so that's my snapshot. And now, since the readers can read things at a certain timestamp, when a transaction wants to write to an object or write to a tuple, they're going to create a new version of that, and that doesn't interfere anybody else from reading the older version. Likewise, when someone is reading the older version and I want to make a new version, I don't have to block on them. Wait till they finish reading. So we're going to allow our transactions to basically get this consistent snapshot without acquiring explicit locks, because again, I've given a timestamp when I started. I can see everything that existed at that time. And then by default, or sort of naturally or implicitly, we're going to get this different isolation level that we didn't really talk about yet, called snapshot isolation. And again, that just means that I'm viewing the database as it existed at a certain point in time. So one of the big things that was touted about MVCC when it came out in the 1980s is that it could support what are called time travel queries. Right? So the idea is like if I say, run this query for me, but on the database as it existed 3 weeks ago. If you have all the versions, because you didn't do any garbage collection and clean things up, then that's trivial to do, because you just figure out, OK, what's a timestamp from 3 weeks ago? Let me go view the database at that time. Postgres originally shipped with that feature. Right? That was one of the big things they were touted when they came out in early 85, 84. That was like one of the original design points of Postgres, is that, oh, we can do time travel queries. In the 1990s, when they first started building out the open source version, or improving the open source version that came out of Berkeley, one of the first things they did was get rid of the time travel thing, right? Because again, if you don't do garbage collection, you run out of storage pretty quickly, right? If you're not familiar with the history of Postgres, so Postgres was an academic project at Berkeley. Anyone can guess what the first language Postgres was written in? What? He said C. No. Basic? No, not that bad. Or worse, meaning what? Close. Lisp. Right? And what it would do, it would take list, then they run a compiler that converted the list into C, and then compile the C. And they realized, well, this is stupid. Let's just, why are we wasting our time on list? Just write it in the C, right? And so there was a academic version of Postgres, and then Stonebraker started the company. I think the first version was called Montage, then Monet, and then they got sued for that, and then got renamed to Illustra. And Illustra got bought by Informix. So the first version of Postgres that came out of Berkeley became this startup that got bought by Informix, then merged in, which Informix got bought by IBM. Like you see how these things get just eaten by the bigger companies. But then the reason why it's not called Postgres now, the official name is PostgreSQL, is because in 1996, 2 grad students took the original academic code, removed all the quell stuff, and added SQL to it. And then a bunch of people started picking up and actually started using it. And one of the people that actually started making a lot of work on Postgres is this guy, Tom Lane. He's CMU alum. He still lives in Pittsburgh because he was a day trader and needed a database. And they started working on Postgres and it took off from there. And so he worked I think he was part of the team that took out time travel queries in like 99. All right, enough history. All right, so here's an example of MVCC. So now we have in our database, now we see we have some additional fields here. Right? Last class when we talked about OCC, we had this write timestamp to say what was the timestamp of the transaction that wrote this record into the main table. Right? But now we have this additional column here. We're going to keep track of the version number. Now this is not something you actually would materialize in a real database. I'm just showing this for the illustration, right, to say what version we're actually looking at. But you wouldn't actually store this. The way you keep track of the versions is through these additional timestamp fields. Just like OCC had write timestamp, now we're going to have a begin timestamp and an end timestamp. And that's going to scope the visibility range of when a version is actually visible. All right, so now when a transaction starts, it calls begin, we have to assign a timestamp. We have to assign its begin timestamp because it needs a consistent snapshot. It needs to know what timestamp I should use to view versions, right? That's different in OCC. OCC gave you a timestamp when you went to go commit. In MVCC, you need to have a timestamp when you start because you have to know what you're allowed to see. So now when I do a read on A, again, ignoring how I find this object, like through an index or whatever, but I'm going to land through version A0 for this tuple, and I'm going to be able to read it. I should also point out that the end timestamp is infinity or null or whatever, just to indicate that this is the latest version. It's not bounded, like the end timestamp scope is infinity. So we can read this version, that's fine. T2 starts, it gets timestamp 2. Now it wants to do a write on A. And so in this case here, I'm going to create a new version of the tuple. Again, assuming it's making a complete copy of it. And then now I'm going to set the begin timestamp to be the timestamp of my transaction T2 when I started. And then I'll set the end timestamp to, again, infinity or null or whatever. And I install the new update in the value. But now I need to go back to the previous version and set its end timestamp to be my timestamp, right? Because now that bounds any other transactions that comes later on, they'll know that if my timestamp is greater than 2, which it has to be because we've assigned 2 to T2, that if they go start looking in the database and they see A0, say their timestamp is 3, well, you look at begin timestamp and end timestamp, 3 is outside that range, so therefore you know that A0 is not visible to you, the transaction, and therefore you would follow down and see that the next tuple has the next version has timestamp between 2 and infinity. 3 is greater than 2, less than infinity, so this is the version you'd actually want to see. All right, so what's missing though? How would another transaction know that this is actually a committed version, right? So additional thing we have to maintain is a transaction status table, where we just keep track of here's all the transaction IDs of the transactions that are active in my system or running in my system. Here's their timestamps, so they were signed when they started, and then you have the commit status or what's happening with them. Are they aborted? Are they committed? Are they cleaned up? Right. So we'll also maintain this table as well. So now the idea is like if a T3 shows up and says, should I be able to read A1, depending on what isolation level I'm running at, if I only want to see committed changes, then I know I should be looking at A0. If I'm allowed to read uncommitted changes, then I could read A1. And I would look at this status table to tell me whether is this transaction finished or not. Then we switch back to T1. T1 does read on A. And in this case here, we can just read the same version that we had before, right? And this gives us that repeatable read guarantee that we wanted. And then we can go ahead and commit, right, for both these guys. Straightforward? Now, one thing I didn't mention is how we actually find the different versions for a logical tuple. We'll cover that later on. Yes?
If a transaction's like, say the third transaction running, and it wants to access A at some point, like, say the third transaction starts for transaction A1, like between A0 and A1, and then tries to read A, will it read based off of its own start timestamp?
So going back here. So say there's a transaction 0.5, right? So what should 0.5 see? Well, when it reads A, it's going to read, it'll read the A0.
Even if at that point A1's already written it.
So A2 does it right here. So you're saying even if A1 does it right?
So if A1 writes and then A1.5 reads A at some point, while A0 and A1 both exist, will it read A?
It'll read A0 because A0, again, the 0.5 is the timestamp that gives me what's the consistent snapshot of the database at that given timestamp. So A1 doesn't exist yet. It might physically exist, but logically at timestamp 0.5, it does not exist yet. So I have to read that older version, which is correct. Yes?
And then for like rolling back, like say a third transaction starts after this, reads A, and then A aborts and A1 aborts and reverts. Will it have? Is there cascading aborts here, or how does that?
His question is, so say we're at this point here where I've written a new version of A. So T2 wrote A1. So then now transaction 3 comes along, and again, say they get timestamp 3. T2 is not committed yet. So again, what should transaction T3 see? Consistent view of the database at timestamp 3. All right, and that means then it should only see committed changes, assuming you're running with that isolation level. So therefore, they won't see A1, they'll see A0 again.
So you also have to track the metadata of whether or not that value belongs to a committed or uncommitted transaction.
That's this. So you would say, all right, in this simple example here, I know that A1 is written by a transaction timestamp 2. Okay, is that committed or not? Should I be able to read that? Look in this thing. Oh, it's still actively running. Therefore, I shouldn't be able to see that. And I should know I need to look at the older version. Now, I'm glossing over how you actually make this efficient, but that's the general idea. OK, so let's look at another example. So in this case here, T1 is going to do a read on A, write on A, read on A, and then T2 is going to read on A and write on A. So T1 starts, gets begin timestamp 1, does the read on A, gets A0 because that's a consistent view. That's fine. Then now it does the write on A, creates a new copy in here. That's fine, just like before. And then again, we have to go update the end timestamp to be 1 to indicate that A0 is bound now, or its visibility ends at timestamp 1. Then we context switch over here, T2. T2 can read A, because again, if we look in the status table for the transactions and see that T1 hasn't committed yet, so therefore we don't see uncommitted changes, so it's going to go ahead and read A0. Then now it's going to go ahead and do a write on A, but in this case here, because MVCC by itself isn't going to protect us about write-write conflicts, right? So assuming there's some kind of two-phase locking going on, so in this case here, we would recognize that because this end timestamp is infinity, we're trying to overwrite this. We go look in the status table and see that T1 has not committed yet. Therefore, we're not allowed to create a new version, right? Because we could potentially overwrite those changes, and that would be an inconsistent view or incorrect view. And therefore, in this case here, it's going to stall and wait. Then when T1 goes ahead and comes back, does read on A, it's going to read the version that error is wrong. Should be down. Error should be here. It should read A1 because that's the one it read before. Then it goes ahead and commits. And now when it commits, say there's a lock on that tuple or an A, that gets released. And then now T2 can go ahead and create the new version and go ahead and allow to commit. Yes?
When is the end timestamp assigned?
So the question is, when is the end timestamp is assigned when you commit? Like when you call commit.
How does A1, how does the end timestamp of A0 to be 1?
So is that for what version?
For A0.
How does it 0 to 1? So going back here, when, there's the end timestamp is the timestamp of the transaction that created it, right? So in this, going back here, so when he does the write, we create a new version here, right? We have 1 to infinity, but now we have 0 to infinity. So again, if I'm following this, think of like a linked list, I'm following the version chain, I would see A0, 0 to infinity. Okay, this must be the latest version, but that's incorrect, right? So it has to go back and set the end timestamp to be whatever its timestamp is. So 0 to 1 exclusive.
Okay, so assume there's no write in the T1, then the end stamp of A0 will be assigned when A1 commits.
So your question is, when is the end timestamp of A1 assigned? Say this doesn't happen. This guy's calls commit. What did I set the end timestamp to? Infinity, because this is the latest version. So is this actually serializable? Raise your hand and say yes. Raise your hand and say no. Raise your hand if you don't know. No, right? Because what should happen? If they was running in serial order, going back here, say we get to this point here. If we were running in serial order, so the end state of the database is A2, right? This guy here read A0, because that was the view of the database it saw when it started. Even though this guy did a write, which it should have seen. But under snapshot isolation, it doesn't. Then when it goes ahead and commits, now it's installing its new change. And so if it wasn't a serial, this is one value, it's kind of trivial. But like, if it was running in serial order, I should have saw, T2 should have saw T1's write and then do its own write, but it saw the write from whatever, transaction 0. So this is because snapshot isolation is susceptible to an anomaly we haven't talked about called the write skew anomaly. Right? And again, the basic idea of snapshot isolation says that you get a consistent view of the database as it existed when the transaction started. So you won't see any torn writes from active transactions, right? You won't see, if they update 5 things, you're not going to see 3 and miss the other 2, right? If 2 transactions try to write the same thing, then whoever gets there first will win, assuming you're not allowed to stall and wait. But this write skew anomaly is a different idea where it's like I got to see the consistent snapshot of the database, but when I apply my changes, it's not equivalent to being if I was running transactions in a serial order. And again, I realized me waving my hands doesn't make any sense. Let's actually look at a really simple visualization. So this was invented by Jim Gray, again, the guy who invented concurrency control and two-phase locking, won the Turing Award in the 90s for all this stuff. Right? He was very good at like dumbing down, simplifying very complex topics in databases. You ever heard of the 5-minute rule? That's from him. You ever heard of P99 latency? That's from him. Or the 5 nines? That's from Jim Gray. All right, so say your database is comprised of marbles, and they have 2 colors, black or white. And you have 2 transactions that want to run exactly the same time. First transaction will turn all the white marbles to black. Second transaction will turn all the black marbles to white. So when they both start running, this is the consistent snapshot that they both see of the database. 2 blacks and 2 whites. So therefore, when the transaction runs, the guy at the top is going to take these 2 bottom ones, flip them to black, and the guy at the bottom is going to take the 2 black ones and flip them to white. And then now, when they go ahead and commit, we end up with this database like this. Again, on a snapshot isolation, that's allowed to happen. Because they didn't take write locks in the whole thing, right? They just updated the things that they cared about. And if it was running in true serial order, it would really be this. First transaction changes all the marbles to black. Second transaction changes all the marbles to white. So they're either all black or all white. So by itself, snapshot isolation is not serializable. And in something like Postgres, there's extra stuff we have to do, but we're not going to cover, in other systems to contort snapshot isolation to make it support serializability. And this is why Oracle, for example, again, when you ask for serializable transactions or isolation level, you're getting snapshot isolation, which would be susceptible to this problem, this anomaly. The original specification for transaction isolation levels that came out in 1992 doesn't mention this problem, right? Defines isolation levels in terms of two-phase locking, right? Read uncommitted, recommitted, repeatable read, and serializable. But again, as I showed that graph last class, the isolation levels are sort of this branching thing, and that side branch is snapshot isolation. And I had the guy that actually was the author of this. He was telling me that he was at Microsoft at the time, and the reason why they missed this skew anomaly is because the one guy forgot to read it or something. Like he was too busy writing some code. He didn't read the spec over carefully, and then they had to come back and fix it later on. All right, so the high level, this is what MVCC is. Again, the idea is that we're going to create physical versions of logical tuples every time they get updated. But it's not just, again, the concurrency protocol like we saw with two-phase locking and OCC. The concept of versioning permeates all throughout the database system. And I showed that diagram of like, here's the different layers of the system. We were building up the stack. But then when I said, now we're bringing in concurrency control, and there's the giant blob of concurrency control assumed all the other parts. That's because all throughout the system, it has to be aware that it's dealing with different versions. And as I said, pretty much every single database system built in the last 20 years, even maybe 30 years, is going to be doing some variation of MVCC. And some are much better than others. So what I'm going to go through quickly is here's all the design decisions you have to make when you say you want to build a multi-versioning system. And you really want to sort of think about, again, what are the implications of these different design decisions about how they're going to affect other parts of the system. So in particular, how you're going to do version storage is going to have a big influence on what happens when you do index management, especially with secondary indexes. Okay? And this is not going to be, this is going to be a brain develop. Here's all these different things you want to do, or you could do. The main takeaway is going to be, and I'll try to say this as we go along, the worst implementation of MVCC that is out there today, at least I'm aware of, is actually Postgres. So you don't want to be doing what Postgres does, despite me loving Postgres. It's actually the worst implementation of MVCC. And we'll see why as we go along. MySQL and Oracle actually do it better. And every other system today, unless they're a fork of Postgres, are doing it the MySQL Oracle way. All right, so I was a bit hand-wavy on how we're actually protecting objects from two writers at the same time. Right? But it's all the same concurrency protocols that we talked about before. Like you still need to bring all that machinery back, right? So if you're doing two-phase locking, right, you still need a lock table. You still need deadlock detection and prevention. You need all the things we talked about in the previous lectures, and the same with OCC. Whether or not you're using a private workspace for the new versions and still doing OCC with the validation steps, that depends on implementation. Timestamp ordering is the basic thing that we talked about before, where like, yeah, I assign a timestamp and I just make sure I commit in that order. And that gives you basic, that'll give you snapshot isolation, but you have to do extra stuff if you want serializability, which we don't cover in this class, but we'll cover in the advanced class. All right, the next thing we got to worry about is how we're actually storing these versions. So I'm just showing again lines that are in a table in PowerPoint. It's not exactly how actually we would implement this. But the way to think about this, the version that you're maintaining for a single logical tuple, it's essentially a linked list. So the version chain is going to have pointers to say, here's the next version that you need for a given tuple. So there would actually be a field with a record ID, more or less, that's going to tell you, here's where to go find the next version as you traverse along the version chain. It'll be a single direction linked list. Right? Double linked list is, for this, you don't really need it. It doesn't really help you. It's just extra maintenance. So the entry point is always going to be at the head of the version chain. But then now the question is going to be, what order do we store the versions? Oldest to newest, newest to oldest. And then what are actually the versions themselves? And where are they actually being stored? So there's three approaches to do version storage. The most basic one is append-only storage, where every single time I make a new version, I copy the old one, insert it into the table as if it was a real tuple, another tuple, and I just keep track of the version chain in the headers. Right? This is what I showed in my example before. This is actually what Postgres does. The next approach is to do time travel storage, which is basically like append-only storage, but instead of storing the new version back in the same table, I'm going to have this separate table that's designated as the time travel table, and I'm going to put all my versions in there. So I'll have a main table that always has the latest version, or the oldest or the newest version, depending on the version chain. That's always going to be in the main table. And then they're going to have pointers to these auxiliary tables, where that's going to put all my versions. And then the last one, which is actually the best one, is that you basically, instead of storing entire tuples, you just store deltas. Like think of like a get diff or diff. So if I have 1,000 columns and I don't update one of them, and the two other approaches, I have to copy all 1,000 columns. But under delta storage, I only store the subset of the columns that actually got modified, and with their new values or previous values. And I'll store that in a separate delta record storage space. So the top one is the worst case. Don't do this, right? Because as you see as we go along, it's going to have a bunch of storage issues, a bunch of, it just makes everything more expensive. The reason why Postgres did this is because the idea of Postgres in the 1980s was there wasn't going to be a write-ahead log, which we haven't covered yet. That's next week. But there was, next class. There wasn't a log that says, here's the changes that I'm making. They said, OK, well, the tuples themselves, that's the change. So recovery would be instantaneous because you just come back, in theory, and then you would have all your tuples that you were modifying and working on just sitting in your tables. Of course, that's really slow because we'll see a bunch of random writes, and that'll be bad. And so the write-ahead logs make a better approach, and they've added that later on. But they still have this idea of like every single time I make a new version, I make a copy of the whole thing. And they have some hacks to try to make this be faster if you can try to keep things on the same page. We'll cover that in a second. So the bottom ones are what you want to do. But we'll go through each of these one by one. So again, append-only storage just says that I have a single table, right? So every table in my database, I'll have sort of one table space for all that. And then now, anytime I make an update, say I make an update to version 1 here or A1 here, I'll make an entire copy of the record down to the new space in the table, install the new value, and then go update the version chain now to point to the new version I just created. In this example here, I'm going oldest to newest. Like A0 is the oldest one. So if I want to find the newest, I follow along the version chain until I find the one that I want. And the pointers are just record IDs. That's going to be a page number and a slot number. The version chain ordering actually has big implications for performance as well. So if you do oldest and newest, that means that every single time I do a lookup, say I follow an index, I look up an index, I get now I get a record ID. That's going to take me to the head of the version chain. Now I got to scan along that version chain until I find the one I want. And again, you're looking at the begin and end timestamp that I showed in the beginning to determine whether the version you're looking at is actually the one you want or not. Right? Newest to oldest is where the head of the version chain is going to be the latest version. So now when I do a lookup in the index and say I just need the latest version, the first thing I land on when I do the lookup is going to be the version that I want. So that sounds great. The downside is now every single time I update a tuple, I have a bunch of indexes. I got to update all their entries now to make sure they point to the new head. If you're doing delta storage, this is actually not a problem because if you just overwrite the head, it's always the latest version, and everybody always points to that. If you do append only, then I make a new version that's now a distinct physical tuple that's in a new location, and now I got to update my indexes to point to that. So these trade-offs, these choices aren't independent from each other. All right, so time travel storage is basically the same thing as append-only storage, except now instead of storing the physical versions in our main table, we have this whole separate table, which is basically just another table, but that we're going to store all the previous versions from this. So if I update this thing A2, I'm going to make a copy of it into the time travel table, and then now I just update the master version in the main table with the latest version that I'm installing here, and then I update the pointers now to point to the next one here. Take a guess why you would do this? Yes.
What if the change affects the index key?
Say it again.
What if the change affects the index key?
What if the change affects the index scheme?
The index key.
Oh, the index key. If you basically treat that as a delete file, like an insert. So if you say you update the primary key, right? Well, is that really, it's almost a philosophical question, is that really the same logical tuple? Well, no, the primary key has changed, so it's really a delete of the old record based on the old primary key, then insert with a new one. So you lose that version chain continuity, but it makes the bookkeeping way easier to do that. If you change the secondary index key, depending on how you're actually keeping track of the secondary index, we'll come to that in a second, you may not have to update anything. I mean, you'll update the entry, but you may not have to. Actually, you have to update the secondary index, but like the value of the index will still be, depending on how you organize it, will still be could be the same.
So you said like those the time travel and previous one like incurs a lot of waste because you need to copy the table, but I don't see you copy like the unmodified B1 into the time travel table. So what was
Right. So his statement is, I made a big deal that append-only time travel storage wastes a bunch of space because you're copying entire tuples, but I have this B1 here, and it doesn't have an entry in the time travel table. What's up with that? Garbage collection. We'll get to that in a second. MVCC doesn't come for free, right? It's a great idea, and it makes things a lot easier, both the implementation side and actually from the application standpoint. But someone's got to clean things up, because otherwise you just run out of space. So you assume B1 has been cleaned up, because no other transaction could. There was a B0, no transaction could see it. There's no extra transaction where that tuple would be visible to it. Therefore, we want to reclaim the space. Yes.
From what I understand, this time travel table essentially is just doing append only change, but in a separate table. So how is this significant better than the append only?
Her question is, this basically seems the same thing as append only, which is correct, where instead of putting it into the main table, you put it in the time travel table. Why is this a good idea, or why is this better than append only? So I'm not saying it's better than append only. What I'm saying is that this comes up in systems that didn't have multi-versioning to begin with. Like SQL Server, when it was originally single version, two-phase locking, and then, we want to add MVCC, you can graph this thing on, still keep all your single version stuff here, and everything still works the same, but now if you want to go see older versions, you have this auxiliary table you can just follow along and read. So in the systems that weren't originally designed with multi-versioning, they would use this approach. So it still has the downsides. You're making entire copies of tuples. Like if you have 1,000 columns, they only update one of them. You still have to pay the penalty. And so this example here, we're going from newest to oldest. So SQL Server works that way. There's another system called SAP HANA. They were doing oldest to newest. So anytime I did a new version, I would make it actually in the time travel table. And then when I ran garbage collection, then I would basically like compaction, then I would promote it to the main table when it was the latest. All right, again, the last one is the delta storage. All right, the basic idea is that now every time I do an update, I'm only going to copy the columns that got modified with their previous values, and I'm going to store that into this delta storage segment. I think MySQL calls it the rollback segment. Basically the same idea. It's like an undo log. So in this case here, the original value of A1 was 111. So again, I realize that there's only one column value, but we assume there's 1,000 columns. You're doing the same thing. But then now, so I'm going to store what the value was before, and with the version information that was here when it was in the main table. Then now I set a pointer to that, and I override in the main table, here's the latest version of this tuple. Again, that's fine. If anyone wants to see the older version, you look at the timestamps and say, oh, this one's not visible to me. You follow the pointer to find the delta segment. And you're basically now like replaying the log to put it back into the state before. Right? Same thing, I updated again. Then I update with a new entry in there. Right? So this looks and smells a lot like the log structure merge tree stuff we talked about before. Right? But in the log structure merge tree, the idea was I was appending the new entries, the new changes that I made. This is the new changes get applied into the main table, and then the previous value gets put into the version storage. Right? So it's sort of the same, but not exactly. But you can imagine you could piggyback, you could combine the two and sort of achieve the same thing. Yes?
So like if I modify so say I have a transaction that modifies A and B together, that's going to be one entry in the delta table.
The question is, if I have a transaction that modifies A and B together, would that be one entry in the delta table? No, because there'd be, again, think of the version chain as like for a single logical tuple, so A or B. Here's the version chain for that. Because think about what would happen if another transaction only modifies B, then they would come along the version chain, they would see changes to A, and they may actually not be visible to it, or like it makes things more complicated. Nobody does that.
But if I have this transaction that modifies both tuples and want to revert it back with the delta storage, how would it know that these two entries for A and B are actually for the same transaction? We need to revert them together.
The question is, if I modify A and B, and so the old version got put into the delta storage, now I need to roll back that transaction. How would I know that these are the changes I made? Because I would see the end timestamp of the entries I'm putting in there would be my timestamp of my transaction. Therefore, I know this is the one I wrote. Therefore, I got to reverse them.
So I basically scan through all the delta changes and find the corresponding timestamp.
The question is, would you scan through all the delta changes and find the corresponding timestamps? In a naive implementation, yes. You can imagine, and actually you'll see this in P4, you could have the transaction record in its own local storage. Here's the changes that I've made. Therefore, you look and see them right away. But yes, to your point, that's a shortcut, right? That's an efficiency improvement. Like you could just say, you can always go back, follow the version chain, and find the version that you created, if you created one. Right? Because the datasets will guarantee that it's not going to clean up or garbage collect or reclaim the changes you made until you've finished. Because that would be, you have other problems. Yes?
Where are the timestamps?
This question is, where are the timestamps stored? I'm not showing the example here, but they'll be in the tuples, the headers of the records themselves. And we'll see this in Postgres. Okay, cool. So now we got to clean things up with garbage collection, because otherwise we're going to run out of space. So the idea is that we're going to reclaim space from the old versions that no other transaction needs anymore. Meaning there's no active transaction that can view a version of a tuple. Therefore, there's no reason to keep it around unless we want time travel queries, which most people don't. The only time that you ever want time travel queries is like if you were getting audited or something like that, right? Like if you're like a securities exchange. Most people don't need it. So we want to be able to reclaim space and be able to use that for new versions and new data. So a version is deemed reclaimable if no other transaction can see it under snapshot isolation, or the version was created by an aborted transaction. Right? We can set a flag and say this thing's from an aborted transaction, should not be installed, and then everybody scanning along can just remove it. So the two design decisions we got to consider are, how do we look for the expired versions? I said one example here. I just keep track of the things you made, and then you go reclaim it. That's one approach, right? And then how do we determine when it's actually safe to reclaim the space or storage for records? So the two approaches to find things is to do tuple level garbage collection, where we'll look at the versions themselves and say, is this thing actually visible by anything that's running right now? Yes?
So I had a question about like the written changes. So if within one transaction we write A twice, will that appear in two entities or just one?
His question is, what happens if you write to the same record twice? If the data system is smart, it would say it would overwrite the first one. Right? Now things get tricky. Like if I allocate space, if my first update updates one column, and I allocate some memory, some space for that one column update, then my next update on the same logical tuple updates 1,000 of them, then it's a little more bookkeeping to manage that. But in general, if you think about it, it doesn't make sense for you to have multiple versions for yourself, right? Because again, when you commit, then you're installing whatever the version that you created. Nobody cares that you had intermediate steps to get there. We'll pop up in Postgres today and see what they do. I think they'll just overwrite it. Again, in Postgres, it's easy because it's append only. In Delta storage, it's harder. All right, so the first type of garbage collection is do tuple level, where again, we're just going to scan through all the versions and try to find something that's reclaimable. And we'll either do this with a dedicated worker, we'll call background vacuuming, or we'll do it while we're scanning data. All right, so cooperative cleaning. And then the other one is what I was suggesting to her, is that you just have all your transactions keep a track of, like, here's the versions I invalidated. Tell some garbage collector, like, okay, by the way, here's things you may not be able to clean right away because there may still be something running if they can see it, but eventually you'll go ahead and clean this up. So in the first case here, the background vacuuming, the idea is that we have a separate thread that's periodically going to wake up and look to find reclaimable versions. All right, and no matter what storage scheme we're using, append only, Delta storage, or time travel, this works just fine. So say we have two transactions, T1 and T2, and they have different timestamps. So now there's this background vacuum thread, our worker. It's going to look at the version numbers from active transactions, and then it's just going to literally just do a sequential scan, look at the begin and end timestamps, and say, okay, I know I have a transaction with timestamp 12, transaction with timestamp 25. Are there any versions of tuples that aren't visible by these two transactions? In this case here, the A100 and B100 are not visible. So we just go ahead and delete them and reclaim the space. All right, well, this sucks if I have to scan my entire table every so often, right? Just blindly looking for things that got modified. So you can be a little bit clever and maintain a dirty bitmap that keeps track of, set a bit to 1 every time a page is modified, since the last time I ran the vacuum. So now when the vacuum wakes up, it says, okay, I just look at my dirty bitmap and only go fetch those pages and go see whether, go prune out anything. I don't know how they were modified because there's only a single bit, but I'll need to look in there to figure out if there's anything I should be cleaning up. This is basically what Postgres does. Right? So there's a bit more cleverness to it. Like if you've updated a table and you've touched 25% of the tuples or 20% of the tuples by default, then the vacuum will go look at it, right? But this is basically how it works. Or you can call vacuum from the command line in the terminal, and that'll kick it off as well. With cooperative cleaning, the idea is that the worker threads are going to know, here's the things that are visible to me, visible to any other active transaction. So now when they scan along the version chain, if they identify any version that's not visible to any other transaction, then you go ahead and prune it. So think of that. There's a global timestamp that says here's the lowest timestamp of any active running transaction. So now as you're scanning along, if you see that anything is less than that, then you know you go ahead and clean it up. And then you just update the version, the index to now point to it. So let's make your scan slower, but now you don't need a separate background thread. Yes?
Do you need to acquire a log on that linked list?
This question, do you need to acquire a lock on the logical tuple? Yes. Yeah. And you update this thing as well, yes. Because otherwise, two people can do the same thing. So this works great, but you still need this thing to kick off every so often, because if I say I update a record, I create a new version, it invalidates a previous one, and then no one ever reads it again, you're never going to reclaim it. SQL Server calls those dusty corners, and you have to, again, every so often, then you kick off the background thread and clean things up. Again, transaction level GC is what I already mentioned. Again, you just keep track of, like, here's all my transactions, here's the things that they modified. So I update A1, A2, create A3, and I just keep track of the old versions there. It could be like a record ID or offset or pointer to say, here's the thing that I invalidated. Go check some later point, right? Same thing, update B, add it to my entry in here. And then now when my transaction commits, I get some commit timestamp. And then we just pass this information along to the vacuum that says, OK, if there's any timestamp less than 10, because that was my begin timestamp, then these things can get cleaned up. Right? This is rare. Most systems do the background thing, the background vacuuming. But again, if you're doing delta storage, it's easy because you don't have to scan the entire table. You just go scan the delta record. Right? And it's easy to clean that up because now you don't want to, like, the problem dependent-only storage as well. As you're vacuuming, now you have holes in your storage space, and you have to compact the pages. And Postgres doesn't reclaim space unless you run vacuum full. So you could have a lot of empty space in there. Whereas if you're doing the rollback segment of the delta storage, like MySQL, you just blow away that delta storage and leave all your tables by themselves. All right, so the next thing we've got to worry about is what our indexes are pointing to, right? So the primary key is easy. The primary key is always going to point to the version head, no matter what storage scheme you're using, right? And as he was asking before, the way you just treat, if someone updates the actual primary key itself, you just treat that as a delete followed by an insert. Because again, conceptually or philosophically, it is a new tuple, right? It's the secondary indexes that are problematic because depending on what the secondary indexes are pointing to, now and depending what my version ordering is, like newest to oldest or oldest to newest, now when I update a record or logical tuple, create a new version, I may have to update every single index now to point to the new version, right? And so I'll post this link on Slack or it's in the slides. The great example of why you need to understand what the hell is going on inside of a database system is this blog article written a few years ago by Uber. Right? The title of the blog article is Why Uber Engineering Switched from Postgres to MySQL. The real title is Why Uber Engineering Switched from MySQL to Postgres back to MySQL. Because they were running on MySQL before, they were having scaling problems like any other startup. They hired some guy who was really big into Postgres, which is fine, it's a good database system. But they didn't fully understand what Postgres was doing on the inside and what MySQL was doing on the inside for their workload. And their workload was actually the worst case scenario for Postgres. So after they deployed Postgres, they realized, oh, that was a huge mistake, and they had to go back to MySQL. And I'm sure they paid millions of dollars to do this. They should have just paid us millions of dollars. We would have told them not to do it and saved them a bunch of time, right? So this again is why even if you don't go off and work on database systems in your career, you need to understand what's going on the inside and what the data system is going to be doing, because when you start pushing these systems really hard, these different design decisions can cause problems. All right, so if you have secondary indexes, the question is, again, what are they pointing to? Right, the key is still going to be the same. The key is going to be whatever the index attributes that I have. The question is, now in the value, what is that? So there's two ideas, or two approaches. One is you have a logical pointer that just says, here's some kind of logical identifier that will help me find, that I can use to find where the actual physical location is for the head of the version chain. Simplest thing to do is just store the primary key. MySQL does this. So when you do a secondary key lookup on that index, you get out the primary key, which you then go probe the primary key index to go find out where the actual physical data is located. Another approach is to choose a tuple identifier. I think it was a synthetic ID. Nobody does this, but because you need to maintain another index for that, and it's not worth it. Postgres stores the physical pointers to the head of the version chain, right? And you use that to go find exactly what you need. So again, say we're doing this. Say we're doing append only newest to oldest. So Postgres is oldest and newest, but the idea is still problematic. All right. So again, when I do look up my primary key index, get object A, I get a record ID, that's a page number and a slot number, as we talked about before, and I land exactly to where I want, the head of the version chain. And I just traverse the version chain to find the version that I want. If I do a secondary index lookup, when I call get A, I get the head of this version chain, or the record ID like this. But again, in OTP databases, you're going to have a lot of indexes, a lot of secondary indexes, right? So now all of these are now going to be pointing to the head of version chain. So in this case here, if now I update the tuple, even if I don't update the attribute that the secondary indexes are based on, because now the head of the version chain is going to change, right, with a new physical address, I have to go update all of these secondary indexes. So Postgres tries to be a little bit clever here. And what they do is, actually Postgres will have for every single version, they will have another entry in the index. But they try to be clever. I think they're called heap-only updates or hot tuple updates, where if the new version, because it's append only, I create the new version, if it's in the same page as the previous version, the latest version, then I don't need to update the index. I just have now in the page itself, when they follow the version chain land in the page, it says, oh, by the way, you came to me through an index, but the version you really want is the next one. Follow that pointer. So Postgres won't actually update the secondary index if the new version is in the same page. And that happens maybe, I think, 40% of the time we've seen in experiments. Right? So it's sort of hack they have to do with because they're dealing with their append-only storage. And what MySQL does is that the second index will give you the primary key, and then the primary key will give you the record ID, the location. So now anytime I update anything down here, I'm only updating the primary key index. I'm not updating the secondary indexes. MySQL is a little bit more complicated because MySQL is because in InnoDB, actually the leaf nodes in the B plus tree, because it's index organized storage, that's actually the data, the tuples. So in that case, when you're not really getting a record ID, if you follow the primary key index, you're getting the tuple. But the basic idea is the same. Yes?
So why adding another layer of indirection would cause problem like the tuple ID? Because like here, if you store the primary index, you will go to another query, which is essentially another level of indirection. But if we add another layer on top of those record IDs, we can redirect all the secondary index to that ID. Then every time you update the record, we update both the index as well as the tuple pointing to it.
So his statement is, instead of, what if I did the secondary index points to a tuple ID, and then there's another lookup table that maps the tuple ID to the physical location. Now everybody, all the indexes just store the tuple ID as the value portion, and I have I have that map to tell me where to go.
Yeah.
It's another index.
But you don't have to go through the B plus tree. This is very...
It's a hash map, sure. It's a hash table. It's another thing I got to maintain, right? It's additional machinery, additional storage space, additional computational space, or computational overhead, where like the primary key index lookup is probably good enough, right? It's just not worth it. Again, B plus tree, with a large fan out, it's not going to be that expensive to do a single key lookup, right? Traverse down, land in the B plus tree, and everything I need is there. Your primary key index actually could also be a hash table as well. I don't recommend it, but you could, right? There's nothing stopping you from doing that. Okay. So with indexes, the multi-version information, like the begin end timestamp, that's always going to be in the kind of tuples themselves. Most systems don't store that in the keys, part of the as part of the index. Again, the exception would be something like Postgres, where they store some version information so that way you don't have to actually traverse the version chain. You can say, you can do a lookup on a key and a version within the index, and then jump to the exact offset or the exact tuple version you want without having to traverse the chain. Because again, if your version chain is spread across multiple pages, now what should have been a single page lookup for one tuple can be a large scan, and that's going to crush performance. That's why Postgres deals with that. But how they're going to handle duplicate keys from different snapshots, that gets pretty tricky as well, right? So say you have a transaction here wants to do a read on A, another transaction wants to do an update on A. So for this guy does the update, he would again follow the version chain and down here to A1, create the new version, and then update the pointer, right? But now they're going to delete A. So in this case here, again, I set a little tombstone in the tuple header, say this thing has been deleted. We know how to do that from previous lectures, right? Then now I commit. Another transaction comes along and wants to insert A. So now I create a new version here, and I need to make sure that if another transaction is running, or in the case of T1, it should see A1 because that existed at the time that it started. But now, if anybody else comes after that, I need to make sure that they don't see. That should be a typo. That should be A3, right? So any transaction comes later on with a timestamp after 30. Should make sure I'm going to make sure they see A3. And any transaction that's still running the past, I need to make sure they see A1. But in my index, unless I store versioning information up in there, they say, oh, go give me key A. If depending on how things are ordered in there, they would maybe land on the first one, and that's actually not the version they want. They would traverse along the version chain and see that thing. Oh, this tuple is actually deleted, but we should actually be seeing A3 at a later timestamp. So there's some additional information we got to keep track in the index to handle this case. Postgres always does it because they want to make sure that you can jump to any point in the version chain very quickly, but if you're not doing that, you still need to maintain version information so that you can jump to when you have discontinuity between same values in the index, but different logical tuple in the database. OK, so I think a bunch of these we've already covered, right? Right, so you basically what happened is that when you do a lookup sometimes, you may get back multiple entries with a single lookup, and then you have to follow the version change to figure out what you're actually looking for. Yes?
So say if I have like something like a B plus 3 index built on some tuple, and I have a transaction modified which actually leads the index B plus 3 to like merge or split, how do I revert back to the original, to like the previous version?
The question is, say in this example here where I call it this A3 does an insert, creates a new version, calls this leaf node to split. How do you roll back to the previous version of the B plus tree? You don't. Well, first of all, say this guy aborts T3. So I need to go clean up that entry in the B plus tree, but you're not going to immediately do that, right? Like you typically say, you would mark this transaction as aborted. You hand that information to the garbage collector, and then some later point, the garbage collectors would come through and sweep through and clean things up, right? And then now, basically the cleanup process in the index is no different than a transaction doing a delete based on the application request. So when the garbage collector goes through and says, okay, here's a bunch of versions I don't need anymore, let me go clean up the indexes, right? Now the garbage collector is calling delete on the index, so if it triggers a merge, then it just happens.
What about if I had a small value for A1, so it's inside this leaf, and then I change it to like a really large value, which leads the value to A1 to move to like other leaf node because it gets bigger, and it needs to be moved to like
other pointers.
Okay, so the question is, if I say, let's not deal with this example here. Say, yeah, so it does an update on A. So say now I update whatever the value that this index is based on to now be really, really big. So what would happen here? Well, in my example here, you don't do anything because well, actually no. So you would treat that as as a delete followed by an insert into the index. So, but sorry. At the moment you do that update, you don't delete from the index because it's still correct at this point because it's still you need to still point to the older version because another transaction may need to follow that along. So all you're doing when the transaction is actually running is that you insert the new entry into the index, and then it would point to, depending on the scheme, either the head of the version chain or if it's Postgres, you point directly to the version you just created, right? So then at some later point, when the garbage collector kicks off, it would say, okay, I got to go clean up A1 here. But I know that I have an index based on this table, and it's based on this attribute. So what was the value of the tuple at this version for that attribute, and make sure I go ahead and delete it in the index if I know that no other version needs it. So at the garbage collection, you would then go clean things up because you still need the indexes to be navigatable so you can find the version that you want based on different attributes. This is what I was saying before, that like when we talked about before we talked about multi-versioning, it was like, oh yeah, here's your index, here's your data. Just have them point to each other, and then you do deletes and inserts, and no big deal, right? Now with the multi-version, you've got to keep a bunch of crap around because someone's got to be able to go see the previous snapshot. So in the garbage collection, that's when we go tidy things up. Going back to what I think you were saying before, though, it sounded like you were saying if I care about the split or merge, how do I revert that back? I don't care about the physical structure of the index while I'm doing all this high-level transaction stuff. So if the index wants to split or merge, I don't care. Right? When I do my operations on it to move data in and out as needed, if it wants to do it, it does it. But I don't need to guarantee when I roll back a transaction that I end up with the exact same physical layout of the index as it exists before the transaction run. I don't care. I only care about the logical contents at this level. Right? There's a separation between what's in the table. There's a separation between what the logical, I'm going to review, what the logical contents of the index are versus its physical layout. And we have the flexibility where the index can change things around as it wants, and we don't care. Same way if the data decides to swap out pages to disk because it ran out of memory, doesn't affect the correctness of our transactions. It'll make things slower, but we don't care about it won't affect correctness. I can riff all day on this. Transactions are wild. It's like there's so many different levels to think about what's going to happen here, what's going to happen there. And again, this is why doing this is really hard, and people pay a lot of money for this. And if you make it distributed, it all falls apart. It makes it harder. Actually, this is basically what it just said, right? The DBS physically is going to delete tuples from the database. All the versions that are logically deleted from the logically deleted tuple are not visible, right? There's no write conflicts here because it's just first writer wins, right? And then we just need to keep track of that. We have a way to say that a tuple has been deleted at some point in time. Usually, you set a delete flag in the header, and then the end timestamp would also demark when the visibility range is, right? And the flag or the tombstone tuple. So I'm kind of rushing because I want to get through actually pop up in Postgres, show you guys some stuff, right? But here's a table we put together a few years ago for a paper on looking at all different implementations of MVCC. And you can see under version storage, the real standout is where's Postgres? Postgres is append only. Hekaton and NuDB and the other ones are doing sort of the same thing, but they are, they're doing this in the context of a distributed system. And Hekaton is doing it because they were trying to do graft onto SQL Server to add in-memory storage for that, right? So append only is going to be a bad idea for most systems. Actually, Hydrise is using append only. They got rid of that and they switched to use deltas like Hyper. Okay, so let's see if my laptop doesn't die. Good. So we're going to do this in Postgres first. Sorry. And then we have time we can do it in MySQL. So we're going to have a simple table that has, I'll log in. Simple table that has 2 tuples. All right. So now in Postgres, remember we saw that CTID field before, right? It was this hidden field. It wasn't actually being stored, but it would just tell you the page number and the slot number of a tuple. There's additional fields for the begin and end timestamp, right? So they're going to call them xmin and xmax. They're basically the same thing, and the number there is going to correspond to the transaction ID that created it. So what we're going to do now, we're going to run 2 transactions. So I haven't talked about how to do isolation levels, but basically in Postgres, when you call begin transaction, you can set what isolation level you want. So we're going to run this one here at the top and read committed, and run the bottom one and read committed as well. So in the top transaction, what we can do, we're going to go do a read on one tuple, right? The first tuple. So again, we're going to get the xmin, xmax, and that tells us the range, the ID, and the value is the actual defined by the user. So now I can also run this command. This is the Postgres idiom, where I can run transaction current or not. Did I hang it? There we go. Weird. Try to connect again. Oh, CMU Wi-Fi. That sucks. Do you know why Wi-Fi is kind of dicey? What was the first university that had Wi-Fi internet? Us. It just has not. It's gotten better over the years. I should knock it that bad. But when I first started, it was dicey. All right. So there we go. All right. Yeah. So here we're in a transaction, and we see we can get our transaction ID 1457. So now when I do an update on a tuple, right? Now if I select it back, now you see that there's a new version let me zoom this down. Now, can I scroll up? Can't scroll up. I can this way, hold up. Right, so when I first did the select, the xmin was 1456, the xmax was 0, and then the record I was looking at, the physical version I was looking at, was at page number 0, offset 1, right? So now when I select it again, now we see we're at page number 0, offset 3, because it created a new version of this, set the xmin timestamp to be my timestamp, set this one to 0. I don't think I can get back to the previous one, but I know it's going to still be there, because if I go to the bottom transaction here and say we first get what our timestamp is, all right, we're 1458, one more than the last one, great. And I go retrieve that same tuple, I see the old version. That's expected, right? Because, again, on the snapshot isolation, I can't see uncommitted changes of the transaction. So this one is C01, right? But now you also see we set the xmax to the timestamp of the transaction up above, telling us that the visibility of this thing is finishing. But I can still see it, right? My timestamp is 1458 because I'm doing a lookup to say, okay, who wrote this? Is that transaction committed? Yes or no? Oh, they haven't committed? Then therefore, this is visible to me, even though the range is stopped, or the range is cut off. Now, let's see whether we can actually read the other version, right? So I'm going to say, you can say, tell Postgres, give me all the data at CTID 03. So I'm telling it, I want to see the data at page 0, offset 3. Should I be able to see it? Yes or no? He says yes. Raise your hand and say yes. Raise your hand and say no. No, right? Because Postgres is enforcing that. Okay, yeah, you know there's something there, but you can't see it. So I'm not going to show it to you. Whereas up above, I can see it, right? Maybe I even need to do this so I can prove that I'm actually seeing it, right? But let's see if I can see the older version like this, right? I can't. Physically, it's there. Logically, the transaction can't see it. All right, so now, so we've already updated the tuple. Let's see what happens when the bottom guy tries to update a tuple, right? What should happen? Hang, yes. Because the top guy up above has the right lock on that tuple, the logical version of it, not the physical version, and therefore the data system says, I can't allow you to go ahead and update. So now, when I come back up here and I call commit, I'm able to go commit, and then you see immediately this thing unlocked. It tells you how long it took. It waited 17 seconds, right? And then this thing's allowed to go ahead and update. So now, what version should the guy at the top see? The thing he just committed. What version should the guy at the bottom see? The one I just wrote? Yep. Right, so now you see we have a new physical version at page 0, offset 4. See the xmin, xmax are now the same as our timestamp, both of them. And then you see the new value that we just put in. But you see that when we did the update, right, this guy set it to 101, or we're just adding 1 to the value. It was 100. This guy set it to 101. But this guy was able to read that update from that other transaction, saw 101, and then updated to 102. Yes?
Why the X max is 1458?
So question, why is it 1458? So why is it not infinity? This is a Postgres internals I don't fully understand. Right? Because if I go ahead and commit bottom one, it's updated. No, I kept it the same.
Is it because the other one committed before this committed?
There's extra metadata they're keeping track of, like the order of things, but the nuances don't really matter. Because now if I run vacuum on the table, right, then it sets it to 0, right? Because it said this is the latest version, right? Because the idea is that I think if it's the same, it has to say, okay, this thing's in flight. I don't know what's going on. Go look at the status table and say what's the status of the transaction. And then when the vacuum runs, it says, okay, well, 1458 equals 14, like xmin equals xmax. This transaction committed, so let's go ahead and set the xmax to 0, because now we know it's the latest version. All right, so we were running with read uncommitted, or sorry, that was read committed. Let's reset the database, and now run transactions under serializable isolation. So again, under regular snapshot isolation, it doesn't handle the right skew anomaly, right? But under serializable, which Postgres' implementation is been shown, it wasn't. I don't think it was correct when it first came out, and then they fixed it, so it is correct. So here now we have our two transactions running, 1462 and 1463. So first thing I'm going to do is have the guy at the top update the update that same record. So I didn't show you returning clauses here, but see how I say update transaction demo set value equals +1 where ID equals 1, and then there's a returning clause. You can put whatever you want there to get back, like here's return also the values that were part of this tuple. You can put anything there, right? You can put in anything that would be in the project output, select output. All right, so now let's go down the bottom. Right? And again, we cleaned everything up. He's seeing the old version, right? And I'm just adding the transaction ID here, 1463. So again, he's seeing the original version of this tuple, and then you see that we set the timestamp got set by the end timestamp got set by the transaction at the top. All right, so now let's have the bottom guy try to update the same tuple. What's going to happen? Say it up. So he's going to hang. Yes. Because again, he's waiting to see the outcome of the transaction up above. He knows that there's a write conflict. In some systems, it would say, okay, you're trying to write the same thing and immediately abort. In this case here, Postgres is trying to wait to figure out okay, what's going to happen from the guy at the top? All right, so now what happens if we commit? What's going to happen? Should the bottom guy be allowed to commit? Make its change? No. Right? Because again, it was able to read the data in the previous version. This guy then updated it. Now it's trying to do an update by reading the previous value of it. But again, even though there's no application code here between my different queries, we leaked to the outside world that the version of the database when my transaction started, the value was 100. Now I'm trying to do an update to it based on that value 100 and set it to 101. But the guy up above already set it to 101. So again, even though I know that these are commutative, you got to think about, like, I got back this data in my application that the value was equal to 100, and then I decided to do something. The data set doesn't know that. It just sees that you're trying to do an update on the something that got updated before, but you read a version of the data that existed before the one of the guy at the top committed. So that would violate the serializable ordering, the serial ordering, and therefore the data system will abort your transaction. All right, one more demo. We can stick with Postgres. I want to see MySQL. Let me show one thing in Postgres. Postgres is going to lie to you too. Okay, so isolation levels are not they're not global, right? So I can have my first transaction at the top. He's going to run with serializable. My transaction at the bottom, he's going to run read uncommitted. Oh, here we go. So the guy at the top is going to read data, right? Sees the data as we expected. Guy at the bottom sees the same thing. That's all fine. Guy at the top is going to update now to the. It's going to update updates the tuple and return back the transaction ID. Right? That's all fine. Now the guy at the bottom does the same update. What's going to happen? He was allowed to do it. Oh, sorry, but he's updating 2. That's different. Sorry. But now when I go ahead and run a select, he's seeing the change that he made, but he's not seeing the change from the guy up above. Well, that's expected, right? Because the guy up above, that's unexpected, because the guy up above made a change to the database. We told Postgres we want to be able to run and read uncommitted. So what does that mean? We should be able to see uncommitted changes. But Postgres doesn't let us see uncommitted changes. If the top guy goes ahead and commits, now when I run this, now I see the change from the guy at the top. So Postgres actually can't even give you read uncommitted, because they have to do more work to make you be able to see uncommitted changes, and it's not worth adding that. So you get read committed for free, even though you're asking for uncommitted. So it's like the reverse of Oracle. Oracle says you ask for something higher, and they give you something worse or lower. In Postgres, you ask for something worse, and they give you something better for free, because they don't want to have to write additional code so that you can just go see uncommitted changes unnecessarily.
What if the above transaction is also read uncommitted? Would it change anything?
This question is, if the top transaction was read uncommitted, would that change anything? No, because the isolation depends on what you see, not how you affect other people. Okay? Yes?
Is it really for free in terms of performance?
His question, is it really for free for performance? It's more like, yeah, so to his point, he's correct. No, so you still have, even though you run read uncommitted, you would still have to write locks to protect 2 guys running at the same time, right? If you don't, so they're already maintaining these timestamps. They would have to write extra code to say, make sure I see the latest version. and that just, it's more code you maintain for this lower isolation level. It's just, from an engineering perspective, it's not worth it. So is it for free? I mean, from an engineering perspective, yes. Performance reason, maybe you could be a little bit faster. But again, the way they're doing, so they're doing oldest and newest. So, and as I said, in the index, they're always going to have pointers to every version, as long as they're not in different pages. So it's not like if I was doing oldest and newest, where I always had to traverse the version chain, and I didn't have those extra pointers. I always had to traverse the version chain, and therefore I just got whatever the first one I pointed at, and I'm done. Yes, that would be faster. But they're not doing that. They're jumping to anywhere in the version chain. So therefore, you might as well go get whatever the version you were going to get anyway. It's just, from their perspective, the way it's implemented, there is actually not a performance difference. Okay? All right, so again, if you want to play around MySQL, we can do that afterwards. So as I said, the MVCC is super important. It's so important that like even systems that don't support transactions are doing some variation of it, like in the NoSQL systems. And it's not a single decision like, okay, I'm just going to do this one thing and I'm done. You really want to design the system from the very beginning to know I'm going to do with multi-versioning, I'm going to do with transactions, and that's going to affect all parts of the architecture. All right, so next class, we're talking about logging recovery. Basically now, if we crash, how do we come back? So next class is how do we prepare ourselves for a crash, and then next we talk about how do we deal with the crash, okay?
I need something refreshing when I get finished manifesting. Too cold, a whole bowl like Smith & Wesson. One quart and my thoughts hip-hop related. Write a rhyme and my pen's intoxicated. Lyrics are quicker with a sip of more liquor. Since I'm a city slicker, brain waves are thicker. Rhymes I create rotate at a rate too quick to duplicate. Feel a breeze as I skate. Mics at Fahrenheit when I hold it real tight. Then I'm in flight, then we ignite. Blood starts to boil. I heat up the party for you. Let my girl rub me and my mic down with oil. Record still turns with third-degree burn from one man. I heat up your brain, give it a suntan. So just cool, let the temperature rise. To cool it off with same odds.